Now today I'm going to be dealing with very, very fundamental issues which really need your full attention, because I'm going to try to make clear what the foundations of the modern scientific revolution were as far as they concern the subject of this course. Already last time I spoke at the end about Galileo's distinguishing between primary qualities and secondary qualities, which means really quantity and quality, saying that the goal of science is to study what he called primary qualities, that is, those aspects of things which are measurable and which could be quantified, and that everything else was irrelevant and not the subject of science, and funny, therefore unreal. Once science became the only access to reality, they became unreal. And this is the foundation and origin of all reductionism in our modern mentality. In fact, a scientific worldview is very difficult to separate it from reductionism, although many scientists are against reductionism. But it's been inbred that we always believe that you can build up the greater by simply blocks from the lesser. And in fact, we don't accept the idea of the greater. We do not accept the idea that the whole is greater than its parts. We do not accept that on a certain level. On another level, because this happens to correspond to the nature of things, of course we do. I mean, none of you would like to have, let's say, something which has to do with beauty or goodness lose its wholeness. The word wholeness still has a lot of meaning for us. And we perceive the world always through a whole which is greater than its parts. Starting, as I've said in this class before, with how we look upon each other, or look upon a flower. Half a flower is not mathematically half a flower. It's less than that. And two halves of a flower do not make a full flower. So it's the reduction of quality to quantity which is foundational to reductionism. And of course the consequence of this for religion is immense. Absolutely immense. Because this really means that whatever we talk about, we really mean that the spirit can be reduced to the psyche. The psyche can be reduced to biological activity to physical activity, and physical activity to the banging of atoms and electrons against each other. That is what really we have in mind. Although we rebel against it, we don't want to come to this, but this is the logic. If you're really a logical person, this is what the Galilean position implied. The Galilean position implied that by studying quantity, you understand the nature of things. And everything which is not quantity is reducible to quantity. And you see how powerful that is. For example, if you say the color red, in physics that means nothing. But if you say 3,420 angstroms, that is the color red. That is, redness itself is not a category. We call it red because it corresponds to a certain wavelength. It's the wavelength that is real. And this must go back, going back to this fundamental distinction made by Galileo. But this was complemented by something else which is even more principial and more fundamental, and that is what we call the theory of bifurcation, which is Descartes' most important contribution to the scientific revolution. Would you close the door, please? Remember, I put 4 names on the board yesterday. The name of Descartes, Galileo, Kepler, and Newton. And it's about these 4 figures that I wish to speak especially. There are many other figures. So these are the giants, the main figures in the scientific revolution. Descartes was a very different type of person from Galileo. He was not a rebel. He didn't have a chip on his shoulders. He was, from a religious point of view, a very pious Catholic. He was a very good swordsman, like in the Three Musketeers. He was sword fighting. You probably don't know that aspect of Descartes. He had a classical Catholic education. And his psychology and many other parts of his philosophy are the continuation of Thomism, the continuation of medieval philosophy. But Descartes brought about the major philosophical revolution in Western civilization. He is the father of modern philosophy. And he provided the philosophical background for the scientific revolution. Although his physics was rejected by Newton. Cartesian physics was totally rejected by Newtonian physics, and Descartes was never considered to be a major physicist. He was, however, a very important mathematician, one of the greatest mathematicians who devised the subject of descriptive geometry, and especially the relationship between mathematics and geometry, that is, arithmetic or algebra and geometry, which had been begun by Muslim mathematicians, but in a very different perspective. For Descartes, the quantification of space was proof that, in fact, out there was nothing but quantity. In high school, you've all studied what we call the Cartesian coordinates. Cartesian, of course, meaning having to the Descartes. That's the adjective for Descartes, in case some of you do not remember. Cartesian means, you don't say Descartesian. The D-E is dropped, because the French do that. Say Descartes Cartesien, and this has come into English from French. So Cartesian means, of course, pertaining to Descartes. Those coordinates, x, y, z coordinates, that is perpendicular coordinates, which we all learn. Which is the point in this Cartesian space can be mathematically measured by its distance, of course, from the three coordinates that exist, x, y, z, and therefore is reduced to number. The geometry is reducible to number or to function. If you're more advanced, for example, you have a sine x function, then of course you get a sinuous curve like this. To be able to equate geometric forms to mathematical functions. The first person to have done that was Khayyam, or at least even before there were a few Islamic mathematicians like Karaji or Kharaji, but Khayyam's work on algebra, great work, which was translated into Latin, was foundational into this. But Khayyam didn't have exactly the same thing in mind that Descartes had in mind. So from the point of mathematics, Cartesian mathematics is a continuation of Islamic mathematics, but philosophically it's worlds apart, and that's for the following reason that I want us to learn now. The foundation of Descartes' philosophy was the search to rediscover certitude. That is between the death of, or at least the eclipse, not the complete death, but the eclipse of Christian philosophy in the 14th and 15th centuries, and Descartes during those 200 years. It was a kind of philosophical wilderness during the Renaissance. All kinds of views were being expressed. But what was very important is that for the first time, skepticism became a major category of European thought. The works of the Greek skeptics were translated for the first time into Latin during the Renaissance. And all of you somewhere in your education have read the essays of Montaigne, another Frenchman, who presented a skeptical view of the world. I said skepticism did not exist in the Middle Ages. The Middle Ages was the age of faith. You might have doubted a particular theological position, like Abelard's questions. But the idea of skepticism, which means doubting either God or the foundations of knowledge, foundations of life, this is a gift of the Renaissance to Western man. Now, Descartes came at a time when Western philosophy was searching for a foundation for certitude. And Descartes sought that in the affirmation of the individuals of his or her own consciousness. And even this, of course, has its background in medieval philosophy. The famous Muslim philosopher, Ibn Sina, the Persian philosopher, writes that if you were to hang me in the middle of the air, where my feet would not touch the ground, my head would not touch anything, I would not have the experience of anything outside, I would still have the experience of myself. And the certitude cannot be taken away from me. This is called the metaphor of the hanging man. In philosophy, in history of philosophy, the metaphor of the hanging man. And Descartes takes off right from there. And he thought that he would be able to reestablish certitude on the basis of the certitude we have of our own consciousness. I might doubt the world, I might doubt, God forbid God, but it cannot doubt the fact that I'm doubting. One cannot evade the certitude of the knowing subject. And so it came up with this famous formula, or Latin saying, which I think all of you know in Latin. About which thousands of treatises have been written since its time. This is probably the most important adage in modern philosophy. Cogito ergo sum. That is, I think, therefore I am. I think, therefore I am. And therefore basing being upon the individual's awareness of himself. The O in the cogito, that's in French is called cogito, is not anything other than the individual I of Descartes. In Latin, you don't have the subject I before the verb. So it's inside the verb, you might say. So cogito is not just think, but I think. Like in Italian and Spanish today, there are Latin languages. French is not like that, it's a Latin language. You have to say, je pense donc je suis, which Descartes also used in French. But I want you all to know this Latin formula. This is one of the most important formulas in Western civilization. If you have not taken a course in history of philosophy, at least you can hear it now. The tradition of philosophers of Europe, if St. Thomas had said something like that, he would have said, cogito ergo est. That is, I think, therefore God is. The S with a capital E. That is, our thinking would be a confirmation of the divine reality. Not only my own existence. By placing the foundations of knowledge upon the individual's awareness of himself, Descartes, in a sense, inaugurated the age of radical individualistic rationalism in Western thought. That is, the final authority of knowing is my individual ego, according to Descartes, the cogito. No other authority, the divine intellect, God himself, revelation, they're not in this formula. I said this formula could have been interpreted in an esoteric way, saying that, as I made many commentaries upon this in my book Knowledge and the Sacred and elsewhere, saying that I think, therefore I am, is in fact a divine assertion. That could be said. That the divine self intellects or contemplates itself, and what we call external reality is a consequence of that. That would be a very profound understanding of metaphysics. But that's not what Descartes means. He means the cogito is Descartes, the individual mind. So with this act, Descartes, in a sense, reduced the authority of knowing to the individual person, which has dominated Western thought since, in both science and philosophy. It's very important for science, in contrast to religion, in which the authority concerning our knowledge and of our consciousness and the external world out there lies beyond the individual. Otherwise, there would be no religion, obviously. It resides in God. God is both the source of the world and the source of our consciousness, what we call our soul, our mind, our spirit. So both poles of consciousness and existence in religion come from God. And although Descartes, I said, was a very pious Catholic, he propagated a philosophy which is not at all a religious philosophy, put it mildly, and caused a great deal of problem later on for Catholic thought and for all religious thought in Europe. Now, to this, Descartes added a second point, which is just as significant, and from the point of view of science, even more important. And that is that Descartes reduced reality to two substances. Everything in the universe is one of two substances, which he called the knowing reality, the subject, and extension, which is the object. And I'm going to put the Latin of this for you on the board again, because these terms have become classical in the West, related to the word real. You can translate as realm here. The knowing realm, the knowing reality. Cogitans. And that which is known, the world out there, which Descartes identified with extensa, with extension. Pure extension. That which can be measured mathematically according to the Cartesian mathematics that he had developed. There is nothing out there in the world of nature which is not pure quantity. So all that we perceive in the world of nature out there, which is not pure quantity, is the imposition by the mind upon nature. It's subjectivized. So all that is qualitative in the universe is subjectivized with one stroke. And although Descartes had a lot of differences with Galileo, they corresponded with contemporaries exactly, and they fought over many issues, on this issue they're expressing the same thing, except Descartes was a much more important philosopher. Galileo was a much more important physicist and astronomer. But in a sense, the distinction of the primary and secondary qualities is a rough way of saying what Descartes was saying much more succinctly philosophically. That is, you have the whole universe consists of two realities. The mind that knows as the res cogitans, and an extension that is known. The world out there is pure quantity. So therefore, everything in a sense that we love in the world is subjective. All beauty is subjective. All form is subjective, unless it's mathematical form. All color is subjective. All taste is subjective. All goodness is subjective. And also it's reverse. Ugliness, evil, everything. And so Descartes prepared the ground for the appearance of a science in which the object studied is nothing but pure quantity. And everything else is relegated to the subject which imposes itself upon that object. That is subjective in a sense. And ultimately unreal. Which is exactly still the view of modern science. Cartesian physics was rejected by Newton. Newtonian physics was modified by Einstein and by Bohr and the founders of quantum mechanics. But this view has continued to this day. In the book which I've assigned to you by Wolfgang Smith, The Quantum Enigma, it's the most brilliant book ever written, actually, on the dilemma of quantum mechanics, because it still suffers from bifurcation. That is, the foundation of quantum mechanics is still this idea that the things out there banging against each other, and it's we who know them as a subject. And therefore the interaction between the two is always difficult. And scientists don't want to think about it. Actually, Descartes, being a philosopher, had to think about it. Of course, he believed that God had created, he believed in God. God was up there. Actually, instead of reduced to a deistic position already. But God was up there having created both of these. But these are completely different. So the question is, how can we know? How can the subject know the object? Since Cartesian dualism, the bifurcation is another name for dualism, it's called Cartesian dualism, is the most profound dualism that characterizes the modern world. There are many other forms of dualism, body and soul and this kind of thing, male, female. Of course, we live in the world of many kinds of dualism, yin-yang, all of these things. But this is not yin-yang. This is not that kind of dualism. These are not complementarities. This is what you could call a complete and extreme form of dualism, because this is totally different from this. This is totally different from that. This is not a speck of the res cogitans in res extensa. There is no consciousness out there in nature. It's all here. And vice versa. It's not like there's an element of yin and yang. There's an element of yang and yin. Yes?
But this res cogitans, it only perceives or understands quantity, that
No, not necessarily. No, it doesn't only understand quantities. It can only know God. Descartes accepted that. But out there, there's nothing but quantity. And so when the res cogitans perceives other things than quantity, it is imposing itself upon that outside. So the question I said is, how does one know the other? That has been the problem of Western philosophy for the last 400 years. In a sense, Descartes cleaved subject and the object in such a way to create cleavage that nobody has ever been able to put together in Western philosophy except by denying one of these two. For example, all materialistic philosophies in the West, from Bayle to Feuerbach to Karl Marx to Professor Skinner of Harvard University, they said this is actually an illusion. In fact, the world is nothing but this. It's materialism. The other half were like Bishop Berkeley and others, Hegel. They're idealists. That is, this is unreal. All of German idealists, only this is real. But this is a philosophical issue. The scientists didn't care. Science did not get into these issues. Although materialism is, in a sense, identified with modern science. But from a philosophical point of view, either position could be taken. The important thing was that modern science placed itself upon the foundation of this extreme dualism. And it's gone on for the last 400 years. Right up to our own day. When Wolfgang Smith said that quantum mechanics is good physics and bad philosophy, that's what it means. Because now physics has gotten us to a point where the problems are insoluble on the basis of Cartesian bifurcation. But the Western mind doesn't want to give that up. And so most physicists refuse to think about what they're doing philosophically. And this is very, very important for the interface between religion and science, as you can imagine. Now, to come back to this, how did Descartes solve this? The two complete different substances, two complete different things. How can one know the other? Descartes said that God had created the world in such a way that there would be a correspondence between a particular moment in the res cogitans consciousness and a particular event which he would recognize. And this is called occasionalism, a form of Cartesian occasionalism, which was developed by Descartes' student, very famous French philosopher, Malebranche, was also a theologian, a Catholic theologian. Malebranche is credited with developing this aspect of Cartesian thought, but it's already there in Descartes. What do we mean by that? Here I'm standing looking at you, and you're hearing me. This should be impossible. And how is that possible? Of course, we really don't know how it's possible, but from the point of this philosophy, it would really be absurd, logically absurd, because you are out there, and I'm over here, and I who speak supposedly have the res cogitans as the source of this speech and discourse and knowledge which I'm transmitting to you. And although you also have the res cogitans, but you're separated by the sound system, waves, by my mouth, by your ears, all of these things which belong to res extensa. So how is it possible to know anything? As the answer of occasionalism, Cartesian Malebranchian occasionalism is the following. Famous story of the cock who gets up in the morning and starts to crow, and does so always at sunrise. And the story is that the rooster thinks that by singing, by crowing in the morning, the sun rises. Because one event is always related to the other event. And if you were standing outside, this is a child on a farm, gets up every morning at some hour, early morning in the farm, before sunrise, and sees the roosters, the cocks coming out of the, wherever they are, hatchery, in the chicken coop, wherever they are, and comes out and starts crowing, and the sun comes up. In the mind of the child, there will gradually come the idea that the crowing of the rooster, of the cock, causes the rising of the sun. That is, these two events go together. Now, this brings up the question of causality, which was discussed later on by David Hume, and he denied causality. He said it was all occasionalism. That part of it is not the subject of today. But a part of knowing is that in the same way that these two events somehow are related in our mind together, because when one occurs, the other occurs, but there is no causality between them. God, in a sense, had wound up the universe according to this in such a way that individual human beings who are created to live in that world are able to know events, but not by direct relationship, but because of how the two things are bound together. Again, I'll give you another example. Suppose you have a reel of film here, and the soundtrack is not on the film. The film starts here, you're all looking at it. The soundtrack is on this side. And when Charlie Chaplin opens up his mouth, he is speaking through this, right here. But they go together. You're watching as if Charlie Chaplin is speaking, although the voice is over here, the vision is, the film is over here. Something like that. That is, the world, in a sense, has been created in such a way that it allows a particular person to know the world without any relationality between them, in the sense of knower and known. So this is a very difficult problem, very, very difficult problem, and it's not really very satisfactory, this solution. That's why it caused many people later on to try to opt for the other solution of going beyond Cartesian dualism by dissolving one into the other. That is, either the subject being unreal, there's only the objective material world, and this has had many different forms in Western thought, many different kinds of materialisms. I mentioned 4 very different kinds. Bayle, who was a French philosopher, deeply influenced by Descartes, was a very powerful materialist who rejected the reality of the soul and the knowing subject, saying that the body is nothing but a machine, which Descartes had already said before him. And although Descartes believed in the soul created by God, he just cut that out. And then Feuerbach and Karl Marx, the 2 German philosophers, who developed a very extensive philosophy of materialism, in which the very movement of matter gradually leads to consciousness, which is the epiphenomenon of matter. And then I mentioned these modern sort of behaviorist psychologists who reduce the human psyche to biological and chemical processes. Now you can see, of course, how powerful these forces are still today. Reductionism, the whole question of human cloning, the fact you can, in a sense, reduce consciousness to physical components which can put together and pops out a human being, or who thinks and who knows. All of these have their deep root in what happened 400 years ago with this Cartesian dualism. But what is important is that despite all of the philosophical challenges, despite all of these questions which philosophers were asking, the scientists picked this up and it became a permanent element of Western science to this day. That is, according to modern science, if we take it seriously, there's nothing out there to study except that which can be quantified. You see even the impact of that upon the social sciences. Get a scholarship to study, for example, the pattern of eating ice cream in Washington, D.C. You might get a scholarship very quickly for that from some foundation. And you immediately have to quantify. You have to send a question is and draw a graph that how the graph lets the number of ice creams goes up by July 10th, as if you have to be a genius to spend $100,000 on that. You know, all these unbelievable things that come out in which you try to quantify some kind of event in the social sciences. That's all Descartes, the consequence of Cartesianism. So I can hardly overemphasize for you the significance of what we would call for this course either Cartesian dualism or Cartesian bifurcation. It is Descartes and not Newton or Galileo who really provided the philosophical foundation for modern science. Although, as I said, he was half a scholastic, his psychology was like that of St. Thomas Aquinas, he was a very pious Catholic, but he considered the world of nature to be nothing but extension. Descartes wrote a whole treatise how the body is a machine made of levers and pulleys, and all of these Frankenstein stories and things like that go back to Descartes. And those who followed him, that is, making a body like a machine and then put some electricity in it and it begins to go like that, we all seen in films. All of this goes back to the idea that the body itself, in which the res cogitans resides, is nothing but a machine. Of course, Descartes was proven wrong, but because people thought it was a very complicated machine. That's why he was wrong. And today it's still very prevalent. 89%, 80-90% of all biologists and physicians in America especially think that the body is a machine. It's treated as a machine. The same way that my car and your car can go to the gas station and put the same gas in and it starts going. All of us get a headache. The same pill is given to all of us. It's treated as a machine, not as a unique constitution, as a living being. All of that is accidental. And although we'll talk about that at the end of the course about this, but I must mention, all of the great critical issues which today are tearing society apart come back right to this point. For example, the question of abortion. Is life sacred or isn't it sacred? If it's not sacred, why can't we murder people? Why will the mother go to jail if her baby is 1 month old and she kills it, but 5 months before she will not go to jail? If it is, that's if not sacred. If it is sacred, where does the sacredness come from? Why is it that the same being is not sacred a few months before and then suddenly becomes sacred? Of course, questions with which modern science has absolutely no answer, and therefore it causes unbelievable turmoil in society. And this is just the tip of the iceberg. All of the other issues that are going to come with genetic engineering and all of these things that are coming about. The challenge, in fact, more than ever before, what remained of the religious view of life and of the world, and which held society together, that life was sacred for them. You couldn't go around killing people. But this Cartesian view kept the sanctity of the individual, because the cogito, the res cogitans was there. And the church, the Catholic Church, clung to that. The church accepted Cartesianism for a long, long time. And said, all right, the world out there is extensa, let them deal with it. Let them deal with it, but at least the body is sacred, human life is sacred, and it emphasizes so much, of course, that it destroyed practically the rest of life on earth. We're doing a very good job. Because only we are sacred, nothing else is sacred. And so we massacre animals, we cut down trees, forests, so that we can watch football games on Sunday afternoons more cheaply. So it comes down to that. That everything has to do with this Cartesian bifurcation. So I think we will not forget that after what I've said today, the significance of this in all the developments of the last few centuries. Now let me turn back to Galileo. I want to try to deal with all these three figures today. Now Galileo, as I said, was a very different type of person from Descartes. He was a rebel. And he was out there to prove something. Galileo was a very great scientist, a genius, without doubt. One of the great geniuses in the field of science. What he did practically was in two domains. And in this, I don't want to go with the history of science part of the scientific revolution, but just very briefly. First of all, he was the first person in the history of the world who had the privilege or the occasion or the possibility, however you wish to look at it, of looking at the heavens through a microscope. That is, the technology of making lenses had developed in Holland, just preceding Galileo. Again, going back to the work of Al-Haytham, Ibn Al-Haytham, who first studied the property of lenses scientifically. And the Muslims made some lenses and something like glasses, but not a microscope. A telescope, actually, a microscope is the same thing. A telescope. Anyway, these lenses were put together, and Galileo looked at the heavens, and he found the moons of Jupiter. That is, he observed the moons of Jupiter. That is, observed the body moving around Jupiter. And the consequence of that was that the Aristotelian division of the cosmos into the sublunar and the heavenly was broken by Galileo. That is, Galileo showed, at least he thought he showed, that the heavens were made of the same stuff as the earth. That is, they were just material substance. It was not crystalline spheres or angelic substances or heavenly substances or ether or all of these things. That they were, in fact, that is, terrestrial physics was no different from celestial physics. They're both the same. So he, with one coup de grace, in a sense, succeeded more than anybody else to the scientific revolution in secularizing the cosmos. It took, of course, many more centuries for people to actually walk on the moon. But to say, all right, the moon is nothing but a piece of rock. This was said originally by Galileo, going all the way to Jupiter. This is one very important discovery of Galileo. And this is discussed in his one of his two great classical works, Dialogues Concerning the Two World Systems, the Dialogo, in which he pits an Aristotelian, whom he takes to be a very stupid person and himself to be very intelligent, and debating with each other, and shows how stupid the other side is, and therefore the whole Aristotelian cosmos must collapse. The second very important contribution of Galileo was to the problem of motion. The problem of motion. When we live in this world, we have the experience that in order for something to move, force has to be applied to it. That is, nothing moves perpetually in the world in which we live. Suppose you have a bowling alley, you have a very smooth surface, and the ball is there. It is, of course, downgraded and has a slope. It goes down the slope. But it's flat, you have to push it. And no matter how flat the surface, after a while it stops. Or when you're playing, let's say, volleyball, and you throw the ball in the air, the ball isn't going to go continuously. It's going to come down, and then if it's not going to hit the ground, somebody else will have to push it. Now, Galileo is said to have shown this to be false by saying that, in fact, in a vacuum, a moving object will continue to move, and an object at rest will continue to be at rest. What needs force is not motion, but the change in motion. That is the greatest discovery of Galileo in the field of physics. That is force. The mysterious thing that we have a kind of feeling for, that which pushes the volleyball, or the cannon which hits or pushes out through placing a dynamite or whatever it is, blowing up a place or anything that propels a projectile, like using firepower for a cannon, or dynamite to blow up a mountain, or anything like that. That force, in fact, is not related to the velocity, as we think. As, in fact, many previous physicists had thought, both Greek and Islamic, but that, in fact, proportional to the acceleration. And from this comes, of course, the famous F equals ma law, which you've all studied in Physics 1, foundation of mechanics. And from this also comes this very, very mysterious creature that now enters into science, that is mass, and the new conception of matter, which Descartes had already philosophically prepared. Matter, that is an it, which can only be measured quantifiably. There's no quality about it. It appears in formulas, physics formulas as M. You all know the famous experiment at the Tower of Pisa. You've heard about this. That's Galileo went supposedly to the Tower of Pisa. I have a doubt that Galileo went. I'll tell you the story in a moment. And the Tower of Pisa, the leaning Tower of Pisa, it leans in a beautiful little medieval Italian city called Pisa. And you go up, and you're by the window. You can look vertically down. The building doesn't intrude. And it is said that he threw a heavy and a light object down, and they both reached the ground at the same time, which is against our everyday experience. I mean, you can throw an elephant and a piece of Kleenex down a building here. You know the elephant is going to land much faster on the ground. That, of course, because of the resistance of the air. But in a vacuum, they would land exactly at the same time. Now, they said that in order to prove this, Galileo went and tested it. The reason I said this appears very unlikely is that I've been to the Tower of Pisa. I've climbed the Tower of Pisa, where, in fact, Galileo is supposed to have done the experiment. And you think it's like this window, you go out and drop something, and first of all, the wall is this thick. And then you have the window, and the other side of the wall, you have another thickness like this. So how could somebody would have had to hold Galileo like that by his foot and have him drop this, and there's no record somebody was holding him like that. So I have a little bit of doubt that he even did the experiment at the Tower of Pisa, but it's become famous. But whatever it was, he proved a very, very important point. But the interesting thing is that all of this discovery of Galileo was in fact for a vacuum. But we don't live in a vacuum. But he negated our immediate experience of the world by appealing to a very powerful science which discovered an aspect of reality which nobody had dealt with before, that is quantity in a theoretical world of pure vacuum. In fact, F is never equal to ma. You have friction, you have resistance of the medium, you have all kinds of other things taking place, but it was an idealized situation which then again reduced the world of nature as an imperfection of that situation. And soon mathematical models were developed in which you would first of all solve a problem like this in a vacuum and then be able to calculate the changes necessary for the fact that the natural situation is not the same as that of the vacuum. But be that as it may, the result of it was the famous story which Sir Arthur Eddington, one of the greatest physicists of the century, in his book on philosophy and science, wrote. He said, one morning I was walking from my house. I was living in Cambridge University, and they have these beautiful green hills outside of Cambridge, and I saw an elephant sliding down a hill. And I came to my office immediately, and I went to the board. The hill was an inclined plane, therefore with an angle theta, and the elephant was a mass m, and I calculated, in fact, how fast it got down the hill. It gives us a famous example of reduction. Projectile movements, especially of cannons. He worked with the military. Imagine one of the Italian military must have been not the forte of Italy, but he found a few people shooting cannons, and he's worked with them. He was able to come up with very important discoveries of how projectile movement works, which is in fact the most difficult part of Aristotelian physics. I've called it, many other people have called it the Achilles heel of Aristotelian physics. Because Aristotle was unable to explain how in fact projectile movement works, and Galileo was able to solve this problem, and so he had run across an aspect of nature on a completely new basis, that is the pure quantification of the objects of nature functioning in a vacuum, whose laws could then be solved mathematically, purely mathematically, and everything which was different from that was irrelevant, was unimportant. Now, because of the great successes of Galileo, of course, he was also criticized a great deal because that physics had not as yet been tested and proven. And Galileo, if he had remained actually within the bounds of either astronomy or physics, nothing would have happened to him. Whereas, in fact, Galileo wanted to draw theological conclusions from what he had discovered, both in physics and astronomy, especially in astronomy. And so there came the famous trial of Galileo, which is one of the seminal episodes in modern intellectual history, in which the Catholic Church, for the last time, tried to preserve its right to know something about the world of nature. And Galileo, in the trial, said in a famous sentence to Cardinal Bellarmine, was the head of the jury, you might say, of the Catholic jury. He said that the duty of the Church is to enable people to go to heaven, not to know how the heavens work. And Cardinal Bellarmine answered him, saying the duty of the Church is not only to allow people to go to heaven, but also to be concerned with the nature of heaven and earth as God's creation. But of course, Cardinal Bellarmine lost and Galileo won. And that's why we always read, how bigoted the Catholic Church was at that time, how wonderful, liberal-minded and open-minded Galileo was. You know the way that history is written by those who win it, obviously. But scholars are now re-examining this to a large extent, and a lot of things have come out. First of all, what happened to Galileo is that he was confined to a beautiful garden in Rome, where it would cost you now about $1,000 a night to stay in the hotel nearby. So he was not in a very bad position. He lived royally until the end of his life. But of course, this very strong friction with the Catholic Church caused the Church to withdraw from its concern with the sciences of this world, that is, with physics and astronomy, except in terms of modern physics and astronomy. So at this time that they come along the Jesuits, very soon thereafter, who considered themselves to be the guardians of the Catholic Church, but also, in a sense, propagators of modern science. They took Galileo to China. As missionaries, they had the Bible on one side and Galileo on the other side, or someone like Galileo. They were the ones who took modern science to China. They took it to Japan. They took it to India. It was part of their sort of missionary zeal. And they created many universities in America, in Spain, in South America, many other places, in Catholic countries, including Georgetown and Catholic University, both of them established by Jesuits. Other orders in Catholicism, like Franciscan and so forth, were not that much interested in science. But the Jesuits took over Western science as part and parcel, as if it were of Catholicism, which of course it was not. It was not. And so you had the beginning of the long period of contention between the claims of science and the claims of religion. And always when religion would say, all right, now I accept this part is scientifically true and that's the domain of science, then a few years the science would take another step like that, the domain of religion, then they would have a contention for a while. So now you're right, we move back one step, and now religion in a sense is at the cliff. With one more step there'll be nothing left of religion. Because it was only the human soul and the human body was sacred and so forth, and now during our centuries, of course, modern science through modern technology is protruding into the very body and also into the psyche in every way that it can. So this very important story goes back to these two gentlemen, Galileo and Descartes. Now, let me say something about the other two major figures of the scientific revolution, Kepler and Newton, who are very different kinds of characters from Descartes and Galileo, and also from each other, but the two have a much stronger religious sensibility as far as the world of nature is concerned than either Galileo or Descartes do. Kepler marks the most evident intrusion of Pythagorean mathematics in modern Western science. This was essentially philosophically a Pythagorean. His love for mathematics was dictated not like Galileo, who called himself a Platonist, against Aristotle, but had no interest in Platonism whatsoever. Galileo always said, I'm a Platonist. And therefore, he opposed Aristotle in the name of Plato. This was brought out by Alexandre Koyré very strongly. But Kepler was a real Pythagorean. That is, he believed that there was a harmony that dominated the world. And he wrote the book, Harmonique der Welt, that is the harmony of the world, which describes his first astronomical discoveries. And he was a great musician, and a wonderful musician, and he was in playing the violin or cello or something like one of his stringed instruments, that the idea came to him that these vast numbers which Tycho Brahe, his teacher, the great astronomer from Denmark, had assembled in the Royal Danish Observatory on the basis of, again, the Islamic tables of Istanbul, of Taqiyuddin, which had been brought in the 16th century to Europe, and therefore a long tradition of observation, this vast body of observation, must have a simple harmonic answer to it. It must be a clue to all of these numbers. And while doing that, the idea came of the simple cube to square ratio of the areas for the movement of the various planets, which is foundational to Copernicus, to Newton's Principia, and also the idea that to simplify the movement of the heavens, all we had to do was to accept that the heavens were moving in an elliptic fashion and not in a circle. It's interesting how things persist. Galileo, who was an iconoclast of the first order, refused Kepler's view that the heavens could be elliptical. In this point, it was still Platonic Pythagorean, because Pythagoras had said the heavens being most perfect must move in a circle, which is the most perfect figure. And so Galileo never accepted that. But Kepler took this revolutionary step of changing the orbit of the planets from a circle to an ellipse. and the sun is standing at one of the foci of the ellipse, and the Earth and the other planets are moving around it. And so, in a sense, he presented a very cogent and remarkably simple view of planetary motion, which itself was had a very deep religious aspect to it. That is, he himself believed it, that God, through his wisdom, had created this immense system, planetary system, on the basis of very simple laws. Now, from Kepler to Newton is a very quick and easy jump, because the laws of motion of Newton are really the results of the laws of Kepler. The laws of motion, which are the foundation of all classical physics. As for the law of gravitation, universal gravitation, that is also the genius of Newton to realize that you have to have such a law in order for Kepler's laws of the planets to work. It's really pure mathematics. I remember once I was taking some kind of advanced course on celestial mechanics at MIT, and one of the questions in the final exam was to derive the law of universal gravitation from the laws of Kepler. And if you had studied enough mathematics, you could do it. It was not that difficult. Of course, it was difficult when Newton did it because nobody had done it before. So Newton came up with the very, very famous formula that is, all bodies in the universe attract each other. And they attract each other through this law. The force of attraction is the gravitational constant times the mass of one body times the mass of the other body divided by the square of their distance. And now that we know that all the laws of nature are 1 over r squared laws. All the physical laws of nature are 1 over r squared. Any other law we would have a different universe, you might say. And again, of course, this mysterious m comes in mass, which is an idea invented in the 17th century, which is the new idea of matter, not to be confused with prakriti or yin or any of the traditional ideas, even materia in Latin. This is now a purely quantifiable, mysterious quantity which we call mass, which other languages have a lot of trouble translating. If you want, you're speaking my own mother tongue Persian, we finally came up with the word germ, which is an Arabic word, but didn't mean that in classical Arabic texts. And also in Japanese, Chinese, people have a great deal of trouble. The idea of mass is really an abstraction, but it becomes a very important abstraction in physics, and one of the great constants, very, very important constants of physics. I hope to have later on in the course of time a chance to describe for you, in fact, the gradual transformation of the idea of matter from that which was impregnated with spirit and life in traditional cosmology to M, and all the intermediate stages, and of course what that means for the religious view of the world. Now, I want to say something about Newton. Newton, of course, is the greatest physicist of Western science. There's no doubt. He was probably a greater physicist than Einstein. And he was so important that he became a kind of cultural hero. That's why, for example, you have Newton, Massachusetts, and all towns named after him in the New World, and in Australia and New Zealand, and really a person of incredible stature. What he did was he took what had developed from the works of Descartes and Galileo and Kepler and many other people, and synthesized all of these together in what became the foundation of modern science. That is, the scientific revolution reached its peak with Newton. He wrote 2 very important works. One was called Principia, written in Latin, and one was Optics, which was written with a K. In the old days, optics had a K, like physics, which had a K in the 17th century. These are his 2 main works as far as the history of science are concerned. The Principia is really the main work, in which he discusses universal gravitation, how the planets move, and what is the constant of force. And he said it's actually through gravitation that the heavens move. And since this can be studied mathematically, there's no need to think of what is the nature of force. I said once someone asked Newton, because until his time, people believed that it was the angels who made the heavens move. Or the love that moves the heavens and the stars, as Dante said, at the very last verse of Divine Comedy. The love that moves the heavens and the stars. Now, this becomes F. Actually, what is the difference? We don't know what force is. It could just as well have been called the angel or love according to Dante. The great difference is that this is quantified. You cannot quantify an angel or love. But F was quantified. So this gave you a mathematical structure of the solar system. If it didn't go beyond the solar system anymore, for the moment we were within the solar system. So very elegant mathematical treatment of the movement of the various planets on the basis of all that had gone before, and then also the physics of the Earth. That is what Newton did, and you listen to me very carefully, was to bring to its conclusion the steps that were taken as follows. It was first of all the secularization of the heavens, which permitted the heavens to be seen as being simply continuous with the Earth. Secondly, the quantification of the movement of the heavens. Celestial mechanics is called. And thirdly, the application of that to the physics of the Earth. So we start from the Earth, we go to the heavens, which are simply the same thing as the Earth. Then we study the mathematics of the movement of the heavens, and we take that mathematics and bring them back to the Earth, and that's physics. That's modern physics. Did you understand what I said? This is very, very significant for all that comes later on also. Because today we have the belief that the whole universe is nothing but the extension of the physics of the Earth. All the things that Dr. Ahmad spoke to you about, or that a person who belongs to very much to the line of Bale, Feuerbach, and Karl Marx, and people like that, although he was a scientist and not, of course, philosophical Marxist, that led Carl Sagan spoke about the vast expansion of the universe and so on and so on. How do we know about that? We have the presumption, and it's no more than a presumption, that the physics of the Earth applies to the whole of the cosmos. There's nothing else in the cosmos but the forces that we are able to study here on Earth, or in our solar system, which is, of course, a very big presumption. But nevertheless, this is found. That's why cosmology changes so much also all the time. Every 10 years, you have a new cosmology, because it implies immense extrapolation. But what took place, which is with us to this day, was with Newton. Following the two steps that had come before, that is, first of all, the distinction between sublunar part of the cosmos and the heavens was removed by Galileo. Secondly, the laws of heavenly motion were studied by Kepler, of course, on the background of Tycho Brahe, Galileo, and others. And then those laws taken by Newton, systematized and applied to the Earth. And so we get now a unified physics, quantified, which claims to be the key for the understanding of nature, which is now seen as a big clock, totally mechanized. And that's why Laplace, the famous French mathematician, one of the greatest mathematicians of the history of mathematics, who worked in celestial mechanics, who told Napoleon, he said, give me a fulcrum and a lever and I will move the Earth. That is the idea that he could solve everything through formulas of celestial mechanics, which are very elegant formulas. I took a course in celestial mechanics once, and it's an unbeliever how elegant the formulas are from the point of view of mathematics. But nevertheless, the net result was a completely deterministic world according to Laplace. That is, where once you had the boundary conditions, you would know everything inside the world. And these were according to laws which had now been solved mathematically, so they thought. And so everything was known. It was just a question of applying the Newtonian view to various other sciences like chemistry, biology, and to various things. If you're studying the star of a crystal, or some rock, or something else. But the model was already set. And the next 200 years was really an extension of Newtonianism in the West until the model broke up in the late 19th century with Max Planck, in the late 1890s, and with Einstein, and then with Rutherford, and all of the other people who discovered radioactivity and the inside of the atom, and Niels Bohr, the great physicist of the century. One more point before we conclude. Newton, like Kepler, was very much devoted to religion. Kepler was a kind of Pythagorean mystic. Strange enough, Newton was also something like that, but he was not so much Pythagorean as a Hermeticist alchemist. As I told you before, Newton was an alchemist. He practiced alchemy. And he kept it very much a secret because he was the head of the British Mint. And people were afraid that the value of the British gold coin might come down. But he has left us a large body of work on alchemy. He also believed in the divine origin of Scripture and believed that there was an esoteric inner meaning to Scripture that, if understood, would explain to you the nature of the universe as he had explained it through mathematics. And he wrote a commentary on the book of Daniel, which is one of the prophetic books of the Old Testament, you know, the visions of Daniel. And he also was very much interested in the study of the New Testament and other aspects of the Bible. He was a very pious person, and he died being very unhappy with what he had accomplished. And he wrote at the end of his life, he said, I did not want my work to result in a mechanistic view of the world which would cut the hands of God from his own creation. But the consequence of Newtonianism was definitely a deism, either agnosticism or deism. That is, God had been reduced to a clockmaker. Because could God change the 1 over r squared law? Could he change any of the formulae of physics? This became the great question. So you had a kind of determinism, quantitative, mathematical determinism, which now dominated over the world of science. And of course challenged, therefore, many, many tenets of religion, including the question of free will. How are we free actually to act in the world? And all of the other questions of this kind which relate to it. And this is the end of what I've said, but what I've said today is very difficult and very central to the concern of this course. I hope very much you have a chance to go over all the arguments, what each of these four major figures contributed to the synthesis of Newton, and read the Barber book, which deals very extensively with details, which I've left to him. And we're going to start next time with the next development in Western science, that is the question of change and temporality, which leads to Darwinian evolution, and what that implies for religion. So please be sure to read the Barber book before we get there.